I'm going to call this the sequel because we had a little technical difficulty when we were filming the first part of it. So this is going to be in 2 parts. I apologize for that. But maybe that gives you a little break to get some popcorn or something like that in the middle. A little rest. You can take a little rest. What I was explaining was how there's this problem with IR. It's not really a problem, but again, it's kind of like too much information problem. In that the intensity of the absorptions is related to the number of bonds absorbing, but also, and probably more, it probably has a bigger impact, the polarity of the bond. So when you have a bunch of CH bonds, it'll have a big absorption, but that's mainly because of CH bond, there's a lot of CH bonds in organic molecules. However, but CH bonds are not very polar, and because they're not very polar, they don't really individually have big absorptions. However, really polar bonds have huge absorptions. So a single carbonyl in a molecule or a single OH bond in a molecule has a huge absorption. And that's what I want to show you here. The carbonyl bond, I apologize, hay fever. The carbonyl bond has a really big, has a relatively large dipole moment. So you've been learning about that in class. The carbon here would be relatively delta plus, and the oxygen would be relatively delta minus. And what I want you to do is think about electromagnetic radiation, as I indicated in the prior part of this movie, or this video, that you can think of electromagnetic radiation as an infinite number of oscillating electrical and magnetic fields. The magnetic fields are perpendicular to the electrical fields. And what do I mean by an oscillating electrical field? What I'm saying is we have an electrical gradient where one end is negative and one end is positive, and it's constantly switching back and forth, okay? And it does so at a certain frequency. And the higher frequency it makes that switch, right, the higher energy the electromagnetic radiation is. And now, this is very simplistic, all right? We're at the beginning of the course. A lot of people have not taken physics. This is not a physics course. So I apologize to all the physicists out there for this very simple-minded explanation, okay? But another way to think about the transfer of energy is to think about that polar bond sitting in an electrical field. Is there some kind of problem? Sitting in some kind of an electrical field, okay? If we think about the carbon with the delta plus end, delta minus end, I'm just putting it in arbitrarily at this point where the field is positive on the top and negative on the bottom, the way I've drawn it, okay? So you can think to yourself, what would that carbonyl do? So you might say, oh, the negative end is pointing toward the positive pole, and the positive end is pointing toward the negative pole, just the way I drew it. So what should that bond do? What should it do? Well, you might say it would stretch more, right? So imagine this stretching out to meet that, and this stretching out to meet that. What is that? That's an increase in amplitude, and that's really the transfer of energy. The bond that is polar is interacting with the light and stretching out more to a greater amplitude. But it doesn't change its frequency because this is going to change frequency, right? At whatever the frequency of that bond vibration is. Okay, so then imagine the same group at another point in time where the delta minus is pointing toward the negative end of the field because it's oscillating, right, at a particular frequency at 1700 reciprocal centimeters. And the positive end is pointing toward the positive end of the carbonyl. Okay, what would it do? Now, some students would tell me the carbonyl will flip over. Now, remember, the molecules are tumbling, but this frequency, this oscillation is very rapid compared to the translation of the molecule. So you can think of it as not having time to turn over, okay? If it doesn't have time to turn over, what is that bond going to do? That bond's going to compress more, okay? So that's another way of describing the transfer of energy and the fact that the amplitude of the vibration changes, but the frequency doesn't change, because think about this oscillating field, right? It's oscillating at the same frequency as the frequency of the vibration. So it's changing at this certain time, and so it's going to get bigger, get smaller, get bigger, get smaller at whatever frequency that is. Say, and in this case, again, it would be at 1700 reciprocal centimeters times the speed of light, as I described earlier. Okay, So what I want you to realize is that a given molecule like this would give a lot of peaks in the infrared. So a molecule like this, let's make it a little more complicated. Okay. Like that. If we had a molecule like this, what would we expect? Okay. We would expect, first and foremost, to see an absorption for the OH bond. Now, OH bonds vibrate somewhere between 3,200 reciprocal centimeters and 3,400 or 3,500 reciprocal centimeters. So we'd expect a big absorption for that because that is a really polar bond. Okay, what else would we expect? We'd expect a CO absorption at around 1,100. Okay, that's just all I'm talking about right now are the stretching vibrations, not the bending. We would expect that. Now, would we pick up on that? Maybe, but realize it's buried in the fingerprint part of the spectrum. So this again, you would expect it to be around 3,400. There is some hydrogen bonding issues, but we're not going to go over them right now. Okay, we will get to them. This would be at about 1,100. Now you're saying, do I have to memorize all these numbers? Do you have to memorize all these numbers? No. But by the end of the year, you're going to know a lot of these numbers, okay, because they're going to be a part of your life, all right? This bond, again, I'd expect it to be around 1,700, not exactly at 1,700. Different carbonyls are a little different. Their vibrations are a little different. The CHs would be at about, about 2,800 to about 2,900. And you're going to see that a lot because organic molecules have a lot of CH bonds. And then we'd also expect this to be, the CC bonds to be around 1,200. You could look this up on a table, but I don't want you to look it up on a table. I want you to think about these more in terms of their landscapes, their topography. So I always kind of kid around with students and I say, I'm not kidding at all. I'm not kidding. A while back I taught myself how to read films, medical films. I'm not an expert, all right? I kid around. I call myself Nerz-Stormes, lampshade radiologist. It's a joke, but I'm not kidding. There is something very much like reading a CT scan, reading an MRI, looking at x-rays. There's something very similar about this. They are related. They are very, very closely related. So increasingly, I look at spectroscopy as imagery. And the truth is, if you're a good radiologist, you have a lot of images in your head, right? I learned how to read some scans, and I know certain parts of the anatomy simply because I looked at thousands of images. I just kept looking at images, till I knew what a stomach was, till I knew what the kidney looked like. I mean, that may sound silly, but I'm not a biology person. I'm not a medical person. I didn't know the whole anatomy inside and out. But you can learn it. And similarly, chemists really look at these spectra from an image standpoint to some extent. I certainly don't sit like wailing away with tables and numbers all the time. Okay, a lot of times you can just look at something and see what's going on because it has a very characteristic landscape, and that's what I want to teach you. Now, the first compound that's going to come up here, I'm going to show us 3 compounds, or 4 maybe, and you're going to see you're going to be pretty good at landscapes like right off the bat. So I'm going to show you what certain functional groups look like in the IR. Before I do that, I want you to be aware that, because you've learned this in class, I'm sure, to some extent, that what you learned about hybridization kind of carries into IR. So there's a very definite trend for hydrogens relating to the carbon they're attached to. So this is one of the first very specific things I'm going to teach you. When a carbon is sp3 hybridized, this is what we call saturated carbon, the bond will vibrate, as I've said a couple times already, 2,800 reciprocal centimeters to about 2,900. And I'm being very approximate here, and the tables, are a little different depending on the table you're looking at. If, on the other hand, you're talking about a hydrogen that's on a double bond, this bond is going to vibrate at about 16, I'm sorry, I'm on the wrong bond. This is going to absorb at about, I would say 3,000, maybe about 29, high 29s, I'll say 2,950 to about 3,100 reciprocal centimeters. And then, if you have a hydrogen on a triple bond, this is going to absorb at about 3,300 reciprocal centimeters. Okay? Now, what's the trend here that we see? And this is a very useful trend. What you're seeing is this bond strength is kind of, to some extent, reflecting the triple bond strength. So in other words, when you have a carbon in a triple bond, the hydrogen attached to that carbon is also in a stronger bond. It vibrates at a higher frequency, and it's going to absorb at a higher frequency. Realize this triple bond will also absorb at around 2,200 reciprocal centimeters. This CH bond is going to be a little weaker than this CH bond, and it'll be at about 2,950 to 3,100, and it kind of reflects, right, the strength of the CC double bond, which you would find at about 1,660, perhaps 1,640 reciprocal centimeters. And this, 2,800 to 29, is going to reflect the single bonds on the other side. So let's say it's a CC single bond. This would be at about 1,200, as I've mentioned. This hybridization effect is very, very useful when you're looking at the fingerprint region, because even though the CH bonds are not functional groups, they do show up in the functional group region. I meant to say functional group region at the beginning of that. Okay, so the first compound we're going to look at, and there's this thing I like students to know how to do, which is called the unsaturation number, and I'll probably send you a video out on how to do this, okay? But propanol is a saturated compound. And the way we do these spectroscopy problems is we usually work with the formula. Propanols have the formula C3H8O. And what I'm going to say for now is that when you are figuring out the unsaturation of a molecule, which is really the number of double bonds and rings it might have, what you're looking at is you're comparing the formula you have to the formula for an alkene, which is CnH2n plus 2. And for now, I'll just tell you oxygens don't do anything to that formula. So if I had a molecule that had 3 carbons in it, C3, it should be H8 if it has no double bonds, no rings, because that's the formula of an alkane. I have a video on this, and I'm going to send it to you, because I don't know that you've done it in class yet. And we're going to have to learn it in the next couple weeks. An alkene, for example, is the general formula is CnH2n. Okay? So if I discovered that my formula here was C3H6, I would conclude that it had a double bond or a ring in it. Okay? And then alkynes, we have to go over this. This is like a whole lecture in itself. It's a good 20 minutes in itself. Alkynes have the formula CN2N minus 2. Okay? So what this is saying is that when you build double bonds, triple bonds, also rings into molecules, what it does is it reduces the number of hydrogens in the molecule. And we call this the unsaturation or the hydrogen deficiency. If a molecule is deficient in hydrogen, it very definitely has certain structural elements in it, and you have to incorporate them. And you'll kind of see that in the formulas that I'm going to show you. So this molecule is C3H8O. So there's info in the formula. This formula matches the alkane formula for something that has 3 carbons, which means it has no double bonds, no rings, no triple bonds. Okay, think about a ring, right? If you make a ring like that, that's C6H12, all right? It's missing a pair of hydrogens. So I always tell students to think about their models coming around, biting in on the ends in a ring. You have to spit out 2 hydrogens to do that. Rings cause a loss of hydrogens. Okay, in a very systematic way. So the first thing I'm saying is the way this problem would normally be presented is you'd go, okay, the molecule C3H8O. All right, you wouldn't be given the answer. And you would say, okay, what does that mean? That means I have a saturated molecule. Now, if it's saturated, no double bonds, no rings, no triple bonds, that means there's really only a few compounds that would work. The compound is either, and you can think about this, you have to learn your functional groups, okay? It's either an ether or it's an alcohol. Think about that. Why am I saying that? Why am I saying it's either an ether or an alcohol? Because those are the only compounds that are saturated, that have no double bonds, no rings. Okay, so let's take a look at the spectrum. Okay, so here's the spectrum. This is the spectrum of, very typical spectrum of an alcohol. Now, how would you know it was an alcohol? Well, this peak here is screaming OH. Alcohols, or the OH group, are normally absorbing at about 3,400, and due to hydrogen bonding, they will typically give a very broad peak. Now, there are ways to remove hydrogen bondings, but a typical IR will show hydrogen bonding. So we're not just looking at the position, which is at around 3,400 or 3,300. We're also looking at the landscape, and the landscape of an alcohol is a very smooth, broad peak. And this is what I meant. It's like radiology. After a while, you'll have images in your head, and you'll be able to interpret them. Okay, what is this right here? Well, every organic molecule should have this. This is the CH stretching vibrations of the organic molecule. And notice, this is just one OH, and this is a bunch of CHs. Which peak is bigger? This has to do with that dipole effect I was talking about. Now, what's the deal with these CHs? These CHs are all below 3,000. I use 3,000 as a marker for hybridization. If you're below 3,000, that's telling you that they are all on sp3 carbons. Okay, that's consistent with our formula. Notice there's nothing else till I get down in the fingerprint region, and I'm not going to interpret the fingerprint region. Okay, so what do we know at this point? We know it's an alcohol because of the topography. I'm showing you what an alcohol looks like. With this information, even if I just had the spectrum and the formula, there's only 2 compounds that fit the bill. So with the information we interpreted, that tiny bit of information we interpreted, that is, it has an OH, right? That is, the rest of it's all saturated. The rest of it's all, there's no double bonds, no rings, no triple bonds in the molecule. These are the only 2 things that fit it. 1-propanol and isopropanol. That spectrum is actually of isopropanol, but if you realize there are millions and millions and millions of organic compounds that are known, and the idea that in one 1-second or 4-second scan, which is about how long it takes to run an infrared spectrum, you could narrow it down to 2 compounds, that's pretty big news, right? So when you get down this far, then you could interpret a little more in the fingerprint region, or you could run an NMR spectrum and you would know what you had. Now, our next compound, okay, has the formula C6H10. So I want to just give you a little idea about this C6H10. Now again, compare it to the alkane formula. The alkane formula for something that has 6 carbons would be 2N plus 2. So it would be H, 2 times 6 is 12, plus 2 is 14. So this is off by 4 hydrogens, missing 4 hydrogens. Now what this equals 2 pairs of hydrogens. And I want you to work this out with your models, but I'm going to tell you, when a molecule is missing 2 pairs of hydrogens, what that means is that it either has 2 rings. Try this with a model. Take a model, put this many hydrogens in, and see what you have to do to fulfill the bonding requirements of carbon, to get 4 bonds around each carbon. 2 rings, 2 double bonds, 1 ring, plus 1 double bond. This is what it takes to be missing 2 hydrogens, or 1 triple bond. When you make a triple bond with your models, you will discover that you lose 2 pairs of hydrogens. And I'm going to cover this at some point in a very systematic way, but I'm not doing it today. So let's take a look at the spectrum. I want to show you a very big contrast in structure. So let's take a look at this. Okay. Now look at how, in terms of landscape, this molecule that's C6H10 is so different from the alcohol we just looked at. Now what it has in common is it does have a peak at 3,300, and it's very sharp. But look how different the topography is. You don't see that big broad peak. So you start to wonder, like, if it says on a table 3,300, like you look up an alcohol, it'll say 3,300. If you look up an SPCH, it'll also say 3,300. How do you tell the difference? You tell the difference by the landscape. Again, go back, look at this. Okay, look at that peak. That's an alcohol. What is this? This is a classic looking SPCH. In other words, the hydrogen on a carbon that's in a triple bond. Are we okay? Mm-hmm. So what is all this stuff here? Okay, this is a review of the last spectrum. These are CH absorptions. They're at about 2,900. Again, use 3,000 as a barrier. That's 3,000. If they're just below 3,000, they're due to the sp3CHs in the molecule. This should not be shocking to us because organic molecules very frequently have sp3CHs. There are portions. Now, if we truly have a triple bond in the molecule, we should see a triple bond absorption. In other words, an absorption due to the carbon-carbon triple bond. Okay, now if you looked on a table, where would that be? It would be around 2,200 reciprocal centimeters, and it wouldn't be a particularly intense absorption because this bond does not have a tremendous dipole. It has a very small dipole moment because of the lack of symmetry in this. That peak is right here. This is a peak that screams, I am a CC triple bond. So what do I get out of this spectrum? I get out of the spectrum the fact that we have a hydrogen on a triple bond. That means it's a terminal triple bond. It has to be at the end of the chain. There are a bunch of CH bonds that are in the remaining part of the molecule, and this peak does not specifically tell us how to connect them together. And it's also kind of, these two are corroborating each other, and this is saying, hey, we've also got, we really do have that CC triple bond. Okay, so notice you see the triple bond twice. Now this part would not be clear from just looking at this part of the spectrum, and it would require either interpreting this fingerprint region or doing an NMR spectrum. And in a week or so, you'll understand how you would use an NMR spectrum to figure out the rest of this. You might on your own try to draw the number of isomers you could draw that would fit the bill here, and there aren't that many. We actually have really narrowed it down to just a few, though this is the exact spectrum of this compound. All right, let's look at another spectrum. Okay. Now, look at this topography. You're already becoming experts, okay? You should be able to look at this and immediately ascertain that this is an alcohol, because it is an alcohol. That is an alcohol peak right there. All right, now, what's the formula? I want you to, again, let's take a look at the formula for a second. What's my timing so far?
22 minutes.
Okay, I'm almost done. So this is C7H8O. Okay? So, what's the deal here? Okay? Again, use the alkane formula. If it's an alkane, why do we use the alkane formula? Alkanes have no double bonds, no rings, no triple bonds. They have all the hydrogens they could possibly have. So, C7H, what would the alkane formula be? Ignoring the oxygen for now. C7H, it would be 2N plus 2, so it would be 14 plus 2, it's 16, okay? Now look at this. This is very interesting. This molecule is missing 8 hydrogens. That means how many pairs? 4 pairs. And you're going to discover for each structural element, double bond, ring, or triple bond, you lose a certain number of pairs. A double bond, you lose 1 pair. A ring, you lose 1 pair. Try it with your models. A triple bond, you lose 2 pairs. We just showed that. Okay? This is missing 4 pairs. That's a lot. I could write a lot of combinations. You know, I could say, that could be 4 double bonds. That could be 4 rings. That could be 3 double bonds in a ring. You know, I could keep going and going and going. One thing I want you to do, like the light bulb should start going off in your head. This is like a little hint I'm giving you. If you get a really high on saturation like that, you're missing a lot of pairs, think about benzene. Okay, just think about a benzene ring. A benzene ring, which is the most ubiquitous aromatic ring that you find in molecules, so you should always assume it's a benzene ring, at least at first guess. A benzene ring has 1 ring and 3 double bonds. 1 ring and 3 double bonds. Think about that. Okay, 1 ring and 3 double bonds. The ring is 1 pair. Each double bond is a pair. So what is that up to? 4. This is probably an aromatic or something that has a benzene in it. But we're going to look at the infrared spectrum and show you some things that tell you it's an aromatic. Okay, so let's take a look at this. We're going to stop in a minute because this is probably enough to digest for 1 week, or to start to digest. What we expect, if this is truly, this is the spectrum of benzyl alcohol. If this is truly benzyl alcohol, what we would expect, of course, is we would see the OH because it's an alcohol. And we are seeing the alcohol right here. All right, what's going on right here? What is this business? We're seeing the CH groups breaking into two populations. There's the population that is below 3,000. Those are the sp3CHs that we've seen in every single spectrum. And benzyl alcohol does have sp3CHs. Okay, they're right there. But benzyl alcohol also has a number of sp2CHs. And what did we say before? We said that sp2CHs are just above 3,000. Now again, go back, take a look at this. This is what an spCH looks like. All right, now we're seeing sp2CHs right here. Okay? All right, that's an indication that we might have an aromatic. All right, aromatic CHs are at about 3,030 or 3,050. Okay? Now, how would we really know it was an aromatic? Well, the CC pi bonds in an aromatic are at a lower frequency, and someday I'll explain that to you, than a normal double bond, but it has to do with the fact that there's resonance in the ring. The double bonds aren't true double bonds. They're like 1.5 double bond. And 1.5 double bond vibrates at a lower frequency than a full double bond. So a regular double bond would be at about 1660, but something that has resonance would be a little lower. So what we see here at this point, right here, is a peak at 1600. And that's one of the peaks due to the stretching of this ring. So we usually look for a peak at 1600 in the fingerprint region. But one of the things that screams aromaticity are these peaks that we see right here. And these are called overtones. Overtones occur at whole number I'm searching for a word, I'm sorry. So in other words, it'll occur at 2 times or 3 times the frequency, whole number multiples, that's what I was trying to say, whole number multiples of lower frequencies in the spectrum. So in other words, if you had an absorption at, say, these are like at around, I don't know, say 1800. If you have an absorption around 900, okay, there's a remote chance you'll see an absorption at 2 times that and then at 3 times that. The likelihood of that, because it's a larger transition, is relatively low. But these are 2 times some frequencies that occur down here. They're very small. But for aromatics, these are actually bending vibrations. For aromatics, they fall in this kind of clear region and they really stick out. And so they call these the aromatic overtones. They're harmonics if you're a musician. Okay? So when people see this, they go, oh my goodness, I've got an aromatic. And normally what you would say is, I've got a benzene ring. That's what you would say. So everything would fall in place here. The formula being unsaturated with an unsaturation of 4. We know we have an alcohol. We know we have sp2 hydrogens. That's kind of a clue. It might be aromatic. We do see this peak that could be an aromatic, but these overtones are what really tell you have this ring. Now think about this. A benzene ring with an alcohol and some sp3 hydrogens that has a formula of C7H8O. Again, sit down and draw isomers. You're going to find there aren't that many isomers. Now, just finishing up very quickly, I'm not going to do this whole problem. We can work on this maybe next week. But I just want to show you what a carboxylic acid looks like, because some of you guys will have carboxylic acids. Now, what would we expect from this? We'd expect it to have some of the characteristics of the last compound. But what I want to point out is that a carboxylic acid is not an alcohol. Okay, a carboxylic acid is a carbonyl, a C double bond O, right next to an OH. And this OH is really different. Let's go back and look at it. Really different from the alcohol OH. Okay? Being next to the carbonyl completely changes the landscape that you see in the IR. All right, so this OH is in this region, but it gives this very broad kind of multiple humped peak. Okay? Now, what else would we expect if it truly is a carboxylic acid? We would expect a CO double bond. And I spoke about this several times during my lectures. This is at 1700. When you see this very sharp peak around maybe a little above 1700, that would indicate to you that you have a C double bond O. Now, C double bond O is in a lot of functional groups, but if you saw this with this very broad hump that kind of encompasses the CH stretching part, you would say you have a carboxylic acid. Now, why is this super important to you this week? Because this week you're separating acids from bases, from neutral compounds, and there's a very good chance that some of you will have carboxylic acids, and when you finally isolate the compound, you'll see this sort of landscape. So I always joke around a little bit, you know, Bryn Mawr, I know you guys are wild people on the weekends, but this is what, you know, Friday night, good thing to do on Friday night, Saturday night. I'm kidding around about the wild thing, okay? I didn't mean anything by that. But great thing to do on Friday night, this is what I do, right? You could go up on our website and just look at different landscapes and study them and really become a great spectroscopist, okay? So if you go back to our study aids for a minute, okay? Okay, I'm going back to my homepage. So there's a great place on this homepage. So I'm telling you, you could have a T. You should have a T. An infrared spectroscopy T. That would be cool. Or spectroscopy T. All right. This, we have this virtual library here. And one of the really good sites, and you're going to use this on this experiment, is the Integrated Spectral Database. Okay? I'm going to quickly agree to their disclaimer. Okay? I've read it many times, by the way. Okay. But anyway, like say you think you have some compound, like say you think you have butanol. Okay? You can type in the name or you can type in the formula. So say you have a suspicion about what you've got. Now you guys have a list of compounds. So this says it has a number of butanols. So let's say we want to look at 2-butanol. Or say you're just a person who wants to sit in on the weekend and look at spectra. Well, when you look at this list, there's a whole bunch of alcohols, right? So I could look at its all different kinds of spectra, but right now we're looking at IR spectra. So let's say I look at its IR spectrum. All right, that's the IR spectrum of an alcohol. Now notice it has some of the features that we just went over. For example, it has the OH. This is actually non hydrogen bonded alcohol. So however they did this, some of their sample is not hydrogen bonded. But you can see the broad peak due to an OH, the sp3ch stretching. You know, you could just sit around and study these. It's so much fun to do. I'm not being facetious either. Studying images is really interesting because you learn a lot.
You missed.
What did I do?
It wasn't an IR.
Oh, I was like, whoa, that is a weird looking IR. So, like, say, I must have looked at the ramen or something. Yeah. Okay, so there's a butanol. Now, again, what are these? The way they ran these, they're actually, this is kind of interesting. You're seeing a little bit of unhydrogen bonded alcohol mixed in with hydrogen bonded alcohol. And someday we'll talk about that. But typically, when our students run alcohols, they get hydrogen bonding. Okay? So, let's see. So, I mean, you will notice, what the point I'm making here is that when you look at these, you'll notice, now there's a really typical looking alcohol. You'll notice that these look a lot like the spectrum I just showed you for propanol. You'll see that alcohols have a lot in common up in the functional group region, but in this region they're going to look different. This is going to be kind of distinctive looking. So when you think you've got the right compound, you can look it up here and you'll find it should be an exact match. Not like a little bit, an exact match in terms of position and intensity. You kind of study the topography. But I'm not joking around. It's not a terrible exercise to look at, say, 5 alcohols and compare their spectra. Look at 5 ketones and compare their spectra. You'll find they have certain characteristics in common. Okay, so I'll see you in lab. Have a good time this week, a good week of studying.